It's 11:01. That's a very slim margin, but let's go ahead and dive in. So welcome to this Akur8 Academy webinar. I am Tom Holmes. I am Akur8's Chief Actuary for the US region. I'm a fellow of the CAS, and I'm a co-author of the upcoming CAS monograph, Penalized Regression and Lasso Credibility. And those are the topics that we're going to dive into today. As we get started, I will encourage you to use the webinar chat. I'm going to have it open as I give the presentation, and this will give me the opportunity to give maybe some in-time answers to questions and some clarifications as needed. So feel free to drop anything in there, and I will try and answer those questions as we go along. So the first question that you're probably asking is, what is Lasso credibility? It's this new term. It hasn't really been used a lot. So what are we actually going to talk about today? What it is it is a multivariate credibility procedure that is not directly based on an exposure standard, but rather based on a likelihood credibility standard. Of course, this is highly correlated with exposure, but it's not strictly the exposure level. And it can replace one-way analysis, table-based reports. I don't know how many times I used to stare at a table of one-way loss ratios and exposure counts and wonder if they were credible enough or correlated. And additionally, these can be used when there's not enough data to build a traditional GLM. So this is using the GLM structure, but it is a more robust methodology. It's also fast. It requires less time to build than a traditional model, and it is quicker than traditional credibility analysis. I put that as a little star because it is quicker than this analysis when you're using a software like Akur8 that has this functionality built in. And also, it is not just theoretical. So this isn't something that you're going to file away at the end of the webinar. This is something that has concrete regulatory guidance in the new RGLM appendix. If you haven't read that, it was out for comments by the NAIC about a month ago. And so that'll provide new regulation on penalized regression models, including lasso credibility and derivative lasso. And then it's also featured in an upcoming CAS monograph with an accompanying case study. So that's what it is. But let's start at the very beginning. So let's provide the background before we dive into this methodology as a whole. So penalization has established links to credibility. This is something that is true, and there's a lot of literature on this and a lot of past presentations on this. So a lot of these are from people at Akur8, but I'll point out that discussion on credibility and penalized regression with implications for actuarial work. This is the Fry paper that is from 2015, and it really outlined this this connection, but it didn't really provide a strict framework for how to implement it. And that framework is what we're going to go over today. And so this link, as outlined in one of those papers, there is an equivalence. You can set up a model such that the ridge penalty term is completely equivalent to the Bullman K. I think this is it's a special case. It uses the identity link function, but all that to say, we can find that equivalence. However, this penalty parameter generalizes to multivariate model. When it generalizes, it is no longer equivalent, but I'd say that's actually a good thing because it can actually handle multivariate relationships, correlation, handle all of the same things that are handled within a GLM structure. And how that works is we have our normal GLM function, this minimization of the log likelihood or maximization of all that stuff. I get those reversed, but anyways, it's optimizing based on the likelihood, and then we're applying a penalty. That is where we get penalized regression. And it's very, very easy to see this connection in a univariate structure. So here I have a one variable model. I have category A with a whole bunch of exposures represented by that blue bar, and category B that has very, very few exposures as represented by that very, very tiny blue bar that might be only barely visible on your computer screen. We have our lines, we have our observed line in purple, our predicted line in gold, our coefficient in green. And really, when we're modeling with a GLM, we're going to give 100% credibility to this category B. It's going to match the relativity exactly. Now, if you've modeled GLMs before, you probably note that the p-value is probably extremely high. The confidence band might be to the moon, but the coefficient that's produced in the end is going to exactly match this experience. And so what happens if we add a penalty? What happens if we add a really, really large penalty? And so what happens if we add a really large penalty is it completely collapses our coefficient to 0. It's at this level, the category B doesn't have enough exposures. It doesn't benefit the likelihood enough to actually warrant any coefficient at all. So our prediction in this model, this one variable model, is just going to be a strict, just a 0, just an all intercept model. What happens in between is kind of that magic part, where as we tune up this credibility parameter somewhere between no penalty and an extremely high penalty, in this circumstance, our coefficient moves between that fully credible estimate and the null coefficient of 0. And this is really easy to fit into that traditional credibility structure. We have our GLM, we have our 0, we have our Z, which is our credibility weight. We have Z weight on the GLM, 1 minus Z weight on 0. And this is exactly how a credibility standard is applied in a multivariate fashion. So it's very simple in a one variable model. It's very simple to explain. But what I have to stress is that not all models are Lasso credibility. Not all Lasso models are Lasso credibility. So you can't just take your GLM, apply a penalty term, call it a credibility procedure, and say that that's magic. That's just a Lasso model. There are certain specifications you need to do. You need to do a very specific setup to make this model follow as a credibility procedure should. And so let's walk through the characteristics that you need to build a credibility-based model with Lasso. So the first thing you need is only to use ordinal and categorical variables as predictors. So you'll notice there's no continuous variable here. That is on purpose, and that is very, very important. And we'll go over why continuous variables are incompatible with Lasso credibility. We'll also go over what ordinal variables are and how to use them, because it's not widely used, I would say, in actuarial modeling today. We now use the offset in a new way. So the offset is now our complement of credibility. Previously, the offset was used as like maybe your values for deductible factors or things that you don't want to model. Maybe GLM is not the best way to get those coefficients, or maybe you don't have data behind it and you just want to offset it. In Lasso credibility, these variables will be both offset and modeled. And that is a very different approach than the traditional GLM approach, and I would say even a very different approach from Lasso. And then lastly, instead of any type of Bowman, any type of classical credibility standard, we're going to use Lasso penalization as our credibility procedure. So none of these things are new. Lasso has been around for a long time. The offsets have been around for a long time. And our ordinal and categorical variables, I mean, again, that's just a way of encoding. So none of these things are, excuse me, new, but we're going to apply them in a new way. So here we have ordinal and categorical variables. Let's just double check our understanding. So categorical variables, I'm sure everyone has a very good understanding of these. They're categories with no intuitive link between the levels. And so that's all to say, in a vacuum, I'm not going to like draw a line and say diesel is linked to gasoline, is linked to electric, is linked to horse-powered vehicles in this data set. They're just completely separate. Ordinal variables, each level is linked to its upper and lower neighbors. Now, in this case, driver age is a very simple variable. It could also be modeled continuously if you wanted to use that treatment. But this also generalizes to things like A, B, C, D, E, F, G, or maybe hazard groups A, B, C, D, E, F, G. It doesn't have to be a number. It just has to be ordered variables. And so the reason that this setup is very important is because ordinal and categorical variables represent step functions. They both represent solely magnitude. And so when we're modeling, you can see on the right-hand side, we have these categories that are being pulled away from that null relativity. We're saying, okay, A has a little bit of signal, B has a little bit of signal down, E has a lot of signal going up. That's categorical modeling. Ordinal modeling has to do with different steps. So here, an ordinal step might be A through B versus D through G. You might have encountered this as one-hot encoding, thermometer coding. There's a lot of different terms for this, but basically, when modeling ordinally, you can set these groups aside. In derivative Lasso, we just treat everything as its own category, and then we penalize the differences. And so that's what the arrows are here. There's another webinar on derivative Lasso on the Akur8 Academy website, so definitely dig into that later. And so we've identified this ordinal step. We identified a second ordinal step, and then maybe a third ordinal step. So what we've created here is we've created a slope. So C through F is definitely modeled in a slope, but it's made out of ordinal steps. And again, this is important because these represent magnitude, just like traditional credibility. And so what it's doing is it's really having a credibility procedure that's saying this step gets credibility, this step gets credibility, this step gets credibility. And so all of our variables in this model represent the same thing. Slopes are incompatible. They're just a completely different thing. It doesn't really make sense to apply credibility to a slope. It's very unintuitive. And as we'll see later, it will give you some false support if variables are modeled continuously. So another reason that this is really, really useful is that ordinal breakpoints are selected through likelihood. So you have all these ordinal steps. We have all of our A through G. And maybe our model fits this way. It says this is the one that maximizes your likelihood, or maybe it's this one. Maybe it's this particular step, or maybe both. But the idea is that by encoding as ordinal variables, you don't have to make this distinction. You don't have to say, is it the second group? Is it the first group? Is it both? Your model will choose this for you. And so ordinal variables are also a very, very simple method of modeling that requires very, very little, almost no judgment. And so why do I really stress that continuous variables are not a credibility procedure? And I stress this because in a credibility procedure, you should really only have credible deviations that are supported. And in this Lasso credibility methodology with ordinal and categorical variables, every difference is decided entirely by the data. However, if I were fitting maybe a continuous variable, let's say I'm just fitting this linearly, what I'm getting here is that I should surcharge group G and I should give an additional discount to groups A and B. Now, because these are the groups that are credible in derivative Lasso, I'd also say that this is probably a credible fit. Maybe we just don't have a lot of data in A and B, a lot of data in G. This would be a reasonable fit of a continuous variable, but it's giving you false support. Then maybe you decide, oh, I'm going to do this other feature. I'm going to fit it with this curve, but now I have a surcharge for A somehow. And I don't know why that's going up compared to B. It could fit a different level of curve. But in the end, the real power here is that we're really separating what is judgment and what is data driven. And that is an incredibly important part of this process is that when you're using a credibility procedure, it should be entirely data driven, and you should not incorporate this judgment to get maybe false support. So maybe you do think that you should continue this support and G should be surcharged and B should get a discount, but it's not supported by the data. It's not supported by credibility. This is a judgment applied through feature engineering. And in Lasso credibility, you need to apply that after the fact. So it really, really separates what is judgmental and what is driven by the data. Secondly, we have the offset. The offset is your complement of credibility. And so let's look at this a little bit formulaically. I hate having formulas in presentations, but I think this is uh, enough algebra. It's just enough algebra that it'll work. So we have the first line is just the traditional GLM coefficient. We have our intercept, we have our offset term, and then we have our beta x's. If we've created this offset correctly, it can be decomposed into these x1s and x2s. And so what I mean by that is we are both modeling and offsetting for the same variable. So for each level of that variable, for each ordinal step, you can find the level that's being offset, you can decompose it, and you'll get to that bottom line where what you're really modeling is you have your level, you have your offset, and your coefficient for that level. And so what this means is that if I don't penalize these levels, I'm just going to get the estimate from my GLM. Because remember, your GLM treats everything with full credibility. If you're creating a model from that bottom line, I don't care if you're modeling B1 plus offset plus beta 1, it's just going to get you to that GLM result. Again, full credibility. On the other hand, if you crank up that penalty to the maximum, you're going to ignore all of your model coefficients and collapse completely to the offset. And so here is how we get that GLM being weighted with the offset now and not being weighted with that zero, that null coefficient that we were looking at before. And so the astute people here might realize that this equation is not going to hold 100% of the time, but this is the principle behind it. This is what is working in a multivariate model. And this is the idea that you can kind of keep in your mind that it is going to follow this pattern in general. And I think it's a very powerful way to visualize the complex things that are going on behind in the actual fitting of the log likelihood. So again, we're going to go between the offset and our GLM coefficients. And how are we going to do that? We're going to use lasso penalization as our credibility procedure. And so what does this look like? So here is a one variable that is ordinal being fit through lasso credibility. That dark green line represents our original model, and the purple line represents our observed relativities. That light green line represents our lasso credibility model at different levels of penalty, at different levels of smoothness, at different levels of credibility. These are all equivalent terms. And what it's doing is when it's very high, it's reacting to that observed value. And you'll see the blue exposure bars, there's not a lot of exposure in that level. So it's not reacting fully. The optimal penalty term is just saying, we can't treat this data as fully credible. We're not going to move all the way up. However, we can move some of the direction. And as we turn up and up and up the penalty term, it's going to shrink back towards that offset. And so this is what I mean when I gave that equivalence on the last slide. We're going to move between this GLM, this fully credible, and we're going to collapse eventually to that offset in dark green. And so again, the power of this is that it happens multivariately, happens across all ordinal steps in your model, all categories at once. So here are, for example, four different variables that are being really penalized at the same time. We have this one credibility standard across all of our ordinal steps against all of our categories, and it's all fitting together. So what does that look like? Well, in I think a lot of you might have seen this graph. This is a traditional lasso model where we have our coefficient paths as the various different colors moving from left to right as we increase our penalty. All the way on the left-hand side, maybe we have our GLM. It's a penalty that's so small that it doesn't have any effect. And then as you apply the penalty, it shrinks towards zero, and eventually collapses out of the model completely. When we add in an offset, now what we're looking at is the coefficient plus the offset. And now when it collapses, it doesn't collapse to zero entirely. The coefficient that's modeled collapses to zero. But since we have that matching offset, as we were seeing earlier, we're modeling kind of this beta plus this offset term. We're instead collapsing to the offset term. And interestingly, we're collapsing at different rates. So if I were to look at this log of a natural log of -7 level, we see that that bottom variable is completely penalized out, while the others are not. And so I'm going to use this moment to stress that the selection of a penalty term is not a selection of a credibility percentage. It's not the selection of Z, because it differs coefficient by coefficient. And in fact, in a lasso credibility model, you can expect the vast majority of your coefficients to be zero, to indicate no change. And a few will remain and say, these are my credible differences. This is where we can differ. And so I just really want to stress that this selection of a penalty term is not a selection of a Z credibility percentage, but rather this likelihood-based penalty that it has to overcome, that your coefficients have to overcome. And so if I've said that it's a likelihood-based coefficient, it's a penalty, it's this weird thing, then how do we actually pick it? Like, well, what do we do? It's not the Bullman K, it's not the classical credibility number. How do we choose it? And the good news, like I said before, is we haven't really invented anything. We haven't invented Lasso. We haven't invented ordinal variables. So thankfully, there's a lot of data science best practice around picking this penalty term. So if you're using cross-validation, there's this reasonable range of statistically similar penalty terms. And so what this chart shows is on the left, on the y-axis, we have a measure of predictive power. So that the higher we are in this chart, the better it predicts. On the x-axis, we have a log of our penalty term. So really, we have larger penalties as we go from left to right. And on this chart, the red line represents the average cross-validation performance, and the bars represent the range of cross-validation performance across these folds. And so that circle is the high point. It's kind of the apex. But within that range, within this box, we can essentially say, well, these are very statistically similar models. If you move one model to the left and one model to the right, they're very similar. And as a data science technique, you would say these are reasonably similar models, maybe nearly identical in their performance. But as a actuary, you say, well, maybe I only want the more conservative side. And I would recommend this as well. I would only recommend starting with the less reactive side of this credibility procedure, because even though the higher side might be statistically equivalent, I would lean towards conservatism. Now, there are reasons to be more reactive to the data. Of course, we all know there's a ton of exceptions to every rule in actuarial science. But in the best case scenario, always be on the more conservative side. And on that note, I would say that you can be very conservative with this. I will suggest that all penalties greater than the optimal penalty are appropriate to select within this model. Now, why do I say this? Well, this one down here that looks like a really bad model, that's actually our current rates. We are collapsing to what we're currently charging today, what those current relativities are. And so everything in this new blue box is a penalty that's going to select really between current and indicated. It's going to collapse all of your relativities to null. And so what I'll say here is that this is also kind of a way to select between current and indicated to say these are going to be my most credible deviations. You can toggle up this standard. Variables will fall out, and then maybe only the most predictive variables will flow through. And again, as you crank up this credibility standard, it's applied across all of your variables. You can see on the left side, like we saw before, this driver age is starting up, going down, and then collapsing. The variable on the top is really has one step up, and then it's immediately collapsing. And so this one is a deviation, but it's not a very powerful deviation. And then on the kind of the far right-hand side, you can see that this curve goes down, then it gets more simple, and then it collapses. And I see a note from the comments that higher penalty seems to mean something like a limited fluctuation concept. Try to minimize the change from the old model. And yes, that's exactly what's going on in practice, is that it's really only changing where it is most likely, using that to like match the likelihood language of saying we set a very high standard and only these deviations that are important are changed. And this concept of limited fluctuation is going to be really actually a good segue into the next few slides, where I'm going to bring some timely details here of why Lasso. Why are we using this? Why isn't it ridge credibility? Why isn't it elastic net credibility? And that is because Lasso has a lot of benefits with this with respect to limited fluctuation, with this limited change. The first thing, you can read this nice block of text about how sparsity is useful. Sparsity is essentially a measure of simplicity. All things being equal, you would like a simpler model. Less is more. We have so much data right now. There's so many like geodemographic variables. I don't have to list off all the data sets that are available these days, but there's a ton. And what we want is we want fewer predictors to get us the same result or materially the same result. And so why I highly recommend Lasso is that Lasso can assign zero credibility to a coefficient. It can completely collapse it. And this collapsing to zero creates a much more stable model year to year. If you were fitting this in Ridge, every single category would have a slight deviation, and you'd be changing your rates a little bit each year, and maybe you're changing it in the right way, maybe you're not. But with Lasso, it sets that precise materiality standard. It says we're not going to pay attention to these small deviations. We're going to completely collapse to our existing model. We're going to avoid jostling customer rates around all the time when it's not real. Um, and it's just going to be a much simpler model to interpret. Like I said, in a Lasso model, the vast majority of your ordinal coefficients are going to be regularized out, are going to be removed. And so when you're explaining this model and when you're looking at what is important, you really will only have a limited number of coefficients to interpret, and likely only a limited number of coefficients from a limited number of underlying variables. I would expect that when using this procedure, if you have a good rating plan, hopefully most of these coefficients are just collapsed out completely. And so let's talk a little bit about how you get these relativities. So this is kind of the nitty-gritty details. But when you're calculating a relativity from a GLM, you use the coefficient. Now here, there's a continuous variable for age of home, a categorical variable for if it has a fire extinguisher, And really, you're just exponentiating that coefficient times your x. That's your beta x. Um, so this formula in the bottom has a typo on the first line. The parentheses should be at the very end. So it's the exponential of all of those betas and beta x's. And then I've just expanded it out for the last line. So this is what you're used to seeing is we take the coefficient, we multiply it by the beta x, and now we have our rating plan factors. In Lasso credibility, it's worth pointing out that it is a little bit different in that you can no longer separate your offset from your coefficients. Because we've both offset a model, offset a coefficient and modeled a coefficient, we're going to need to incorporate both of those in our estimate of the prediction. And so here on the left-hand side, you'll see the mapping of our offsets and our coefficients that are combined before we multiply it by the x's. So that the betas are combined into one, we multiply it by our x's, and we get our final indicated coefficient. And all of this comes back to that algebraic decomposition that we showed earlier of if you've created your offset correctly, you can decompose it into your betas and x1s, or beta 1 offset, x1, beta 2 offset, x1, and so on. And then using algebra, you rearrange it to just bring x outside of these parentheses. And while I don't really like showing a lot of formulas, we'll move back to the visual and just say this is exactly what's happening there is you can't remove the offset. And just like in this path, our curve is our coefficient plus our offset collapsing to the offset itself. And so here we have our paths through penalization. And this also means that when you're evaluating this type of model, you're not going to want to use the traditional univariate plots that maybe you have before. So on this left-hand side, we have our traditional univariate plot. We have our coefficients and our coefficient in light green. So those are the combination of all the ordinal steps identified by this Lasso model. So in this particular model, you can really see that it's identified one, two, I think just three differences. Just three differences. So again, we've combined all of our ordinal steps together. It's identified one big ordinal step for young drivers. There's an additional ordinal step that gets you down a little bit. And then there's one more ordinal step that goes down to the original, or that low level of your light green. Then a tiny ordinal step in the middle right of this graph. So really, this is what I mean by a lot of these ordinal steps are removed. All of the ordinal steps for like 18 to 19, 19 to 20, 21, 22, 23, all of those have been removed out. But this graph on the left, while it is a little descriptive of what the model coefficients are fitting, I'd say by itself, it is useless. Because I don't know what this is actually going to do to my final relativities. Is this creating a curve that makes sense? Is it creating a curve that doesn't make sense? And so on this right-hand side, we have a relativity plot. And this relativity plot is exactly what it's showing. It's not just showing the univariates, it's not just showing the coefficients, but it's showing the original relativity and your new relativity for this variable. So we've combined everything we know. We've combined the offset, we've combined our coefficients, and now on this right-hand side, we have the dark green being the original model, our offset, the light green being our new model, our offset plus our coefficients. And this is something that I would probably share with stakeholders just to say that our model identified some credible differences really only in the younger side of driver age. The older side, yes, there are some changes, but you can look at the final relativities themselves and decide if that is material. So we built this model. We have our relativity plots. We've run through everything. And so why do we want to do this? Why is this a great procedure to go for? And I would say one of the main benefits to this particular approach is just speed to market. When I say speed to market, it is fast. And I say it's fast when you set it up correctly. And I'll say it's just really a one-step process. And so how can you make this into a one-step process? There are three major considerations that I would say if you want to make this fast, if you want to see the full benefit. One, use your current rating factors as the complement. Use something for the complement that is inscrutable. Because again, it's so important to have that proper complement. Your rating factors are great, especially if you're going to file this. You don't want to spend time justifying your complement. You want to just say, these are my current rates, these are my indicated rates, here's my new rates. The more complicated your complement is, the more scrutiny, the slower, the more this becomes more of a judgmental process. So current rating factors are the easiest things to use. I will say if you're doing this for analysis, even just your current premiums, they'll be offset with the intercept of your model. It'll be inexact because it has expenses in it, but it's close enough to get something quick. The second part is these ordinal breakpoints need to be aligned with the existing rating plan tables or sufficiently granular not to create pre-groupings. So for example, I'm not going through and manually saying, okay, my ordinal breakpoint is driver age 18 to 30, 30 to 45, 46 to 50. Like we're trying to get these groups to be as granular as possible without making computation time extreme and without maybe being too granular for your rating plan. So that's why I would, if you're modeling something like coverage A, you have these buckets in your rating plan. It's like 100,000 to 105, 106 to 110, and all that stuff. Just make your ordinal breakpoints exactly matching your rating plan so you can do a one-to-one match. Last one, parameter tuning follows best practices. The more that you deviate from this process I'm going to show on the next slide, the more complicated it is to justify, the harder it is to really make this that one-step model. So when I say this is a simple model, I mean that there's really one step. So the first step, you identify your statistically optimal credibility standard. This is through cross-validation. There's a whole bunch of packages that do this already. Anything that's doing penalized regression should be able to find this for you already. And you look at this credibility. Do these breakpoints make sense? Are they too jumpy? Do they hop around? Is it giving too much credibility to a level that maybe we have experience in there that is favorable, but I don't really believe it. And this is a little bit more hand wavy, but in the end, if it's too reactive, you increase it. If the results aren't implementable, if they don't make sense, if you think your data is too noisy, you can increase the credibility standard. If it's appropriately reactive, you're done. And so all this step is this chart that I was showing earlier. You find that optimal credibility standard, and you move closer and closer and closer to your existing rates. So all you're doing is being less reactive to the data. It's a more conservative trust of your experience. And actuarially, I think that is a very, very sound assumption to make is when in doubt, stick with your existing rates. I will tell the one actuarial joke that I know again. And by telling this joke again, I'm kind of perpetuating the stereotype. It is how many light bulbs, or how many actuaries does it take to screw in a light bulb? And the answer is I don't really know how many did it take last year. And the idea is that like, yeah, okay, we trust what happened last year. And now you can probably say, what joke did Tom tell last year? Was that one he's going to tell it again? Well, let's break this down a little bit and say why is this fast? Why is this, I think, a huge leap for a lot of analysis? Why is this better than building a normal model or faster? So when you're building a model using continuous variables or like a traditional GLM, this data engineering can get a little bit complex. You have various choices to make. Am I going to cap this? Am I going to floor this? Am I going to use splines? Am I going to like how am I going to model this? In Lasso credibility, it's ordinal and categorical. You really don't have many choices for these two variables. Your categories are categories. Your ordinal ones, you break it up. If you're afraid more, you break it up more. It's really not going to mess up your model to have too many breakpoints. The only thing it's going to do is make it run a little bit slower. So I'd say this is a very fast step to get those ordinal breakpoints. When you're modeling, this is where continuous variables, it's very iterative and very judgmental. And I say judgmental because when you're creating these continuous variables, you're putting in your own type of judgment about what you think the slope is. What kind of slope do you think it is? Do I think it is a linear slope? Do I think it's a log slope? Do I think it goes up in an exponential distribution? Where do I cap it? Where do I say, well, there's no support past this number? Where do I cap my feature engineering? It's very iterative. You're going through over and over and over again, and it's a not a quick process. And Lasso credibility, it is that one step. It's what I showed you on the last slide. You build your models, you can build them in parallel, and then you select your level of credibility, you're done. All of that because there's no choices, no judgment in the selection of your feature engineering. And then post-modeling selections, you're doing judgment on top of judgment. You're saying, okay, I built my feature engineering as an actuary. I think this is what it should be. You hand it off to somebody else and they apply their own judgment saying, well, I know it's indicated, but let me now do my own extrapolation or my own judgment on top of it. In Lasso credibility, it really separates that data-driven step from that judgmental step. And yes, you might want to make some judgment selections on the back end, but you're making those judgment selections once, and you're sure that what you're doing is completely data-driven from the start. So this is why it has these speed benefits, is because it is a really one-step methodology. Then everything afterwards is where you place your judgment. Here's my aside, p-values and continuous variables. So like I said earlier, in this methodology, only these credible deviations are supported. The fit is decided entirely by the data. I could fit this line continuously. I could fit this one. I could fit this one. All of these, if I have data in categories C through F and very little data in A, B, and G, all of these are going to have p-values of less than 0.05. And so I'm bringing this up because Lasso does not allow for p-values. The math just doesn't work out. There are some ways you can try and make like surrogate GLMs. You can try to do some math around that. But in the end, all of those are approximations that have their own issues, especially when using this technique or like a derivative Lasso technique. But what I would say instead is that this approach is more robust than p-value analysis because every deviation is credible. Everything is specifically data-driven. I'm not feature engineering. I'm not creating these kind of what I think the slope should be. It's what steps are identified by the model. So you may get asked, where are my p-values? And I will push back and say, this is a better way. You don't want p-values for this model. This is more robust. And I'm going to drive this point home through a straw man argument. I know that this is a weak argument, but here are two GLMs. Every variable in both of these GLMs has a p-value below 0.05. And maybe one fits better than the other. One of them kind of shoots to the moon on the left, one of them shoots to the moon on the right. But in the end, if I look only at p-values, I say these are both reasonable models. I know judgmentally that they're not. And so really what you're doing is you're applying judgment to say, I think that this isn't the right way to do it. You can make some more intuitive changes. Maybe you fit a more complicated term. But in the end, the reason that you would say that tail whip at the end is not reasonable of this blue line of this simple GLM is judgment and not p-values. So all of that to say, this green line here is a penalized GLM using an ordinal approach. This is a derivative Lasso model, and it is all data driven. So it really separates those two. So don't be afraid to push back when people are afraid that Lasso doesn't have p-values. That being said, as we fit this model, you will probably want to apply judgment, but this allows you to really separate your judgment from the modeling process and be very clear about where you're doing it. So it's completely reasonable to say, well, I identified these stepwise credible differences from C to D to E to F. We don't have very many policies in G, and actually we just really want to continue this trend. We know judgmentally that G is worse, and maybe we know judgmentally that A and B are better. So this allows those with business knowledge and knowledge of the industry to really come in and apply their judgment very clearly off of a completely data-driven starting point. So I'll just kind of reiterate there that the other power of this is that you have that data-driven step, you have that judgment-driven step, and they are separate so that you can very quickly do the data-driven step, and then judgment can take as long as you want. But it will certainly take, I would say, less time than if you were applying judgment and then had to go back and see what judgmental decisions were made in the first place. And this isn't to say that p-values are bad. They're useful after the fact. But I think that the application is, in my mind, a little bit more robust. So if we were making this comparison of p-values to Lasso credibility, these variables that are insignificant, you manually remove them when they have a high p-value. In Lasso credibility, you have that standard where they will just be collapsed and removed completely from the model. When it's significant, you can really get very close to full credibility using Lasso. In a GLM, you're always at full credibility. You're saying, this is my observed relativity. And as we'll see later, well, as you'll see if you read that monograph when it comes up, Lasso can be very, very close to a GLM when the data is very credible. The difference here comes from these partially credible segments where maybe you're mostly confident. Maybe it's a 96% confidence. Your p-value is 0.04, 0.03. In an unpenalized GLM, you're going to make some manual adjustments. Maybe it's 0.06. And you're like, oh, I don't know what to do with this. In Lasso, you have that set materiality threshold that removes things that are going to hurt the model. And then for these ones that have some signal, you get an amount of credibility. So you might have a very small segment that might have a p-value that's pretty high. In Lasso credibility, maybe it says, well, we can trust this like a little bit. We can't trust it very much. You can't possibly trust the full indication, but you have enough data to move a little bit towards it. And that's really the key of this methodology is credibility. It's moving towards indicated in this multivariate framework. So this has all been pretty like the backup. Again, the setup. Please drop more questions, comments in the chat. We have one more section to get through. And that section is a preview of what this monograph case study will look like. This case study is set up to refit a countrywide model. And so this is a very US specific project, but I think that this setup will generalize to a bunch of different geographies and a bunch of different situations. So we set this up with a base modeling data set that's just this huge combination of data. And then we have a subset that represents what we would consider a large state in the United States, maybe a medium state, and then small states. Now, these have a lot of rows in them, maybe like 500,000 rows, 300,000 rows, 100,000 rows. But this is all to say we have these different sets, and all of these different sets of data have different relativities. So for example, we have our base data, where there's an underlying relativity for this multi-policy discount. And then all of our large, medium, and small states have differences. And this is something that we very commonly see in the United States. You'll fit a countrywide model that has all of your data. It tells you that you have one relativity. But when you dig down to certain geographies or certain subsets, the underlying relativity is different. It changes. And so we are using simulated data so that we know what these differences are, and we can test and observe how this approach reacts to these relativities, how maybe it doesn't, and how maybe a good or bad complement can hurt or help your model. So we did this for categorical variables. We also did this for GASP continuous variables because we have all these assumptions behind it that allow us to use continuous variables. Now I go through all of the reasons why this is only applicable to a simulated case study. But the idea is that I wanted to make sure we compared GLMs and this penalization procedure using the same feature engineering, the same benefits. And ordinal just simply it does not work in GLM. So here we have different slopes for driver age. And again, we're comparing to the true relativities. We know what these are, so we can see what's noise, we can see what's real in our data set. So what the case study does is it starts by modeling a countrywide data set using both GLM and Lasso. And in this particular example, we have 3.5 million rows, I'm pretty sure. And these models are immaterially different. I think the lift chart here is the spread on the lift chart is like 0.002 or something like that. They're really the same. The Lasso does have slightly different results, but these coefficients, again, immaterially different. I think when you're rounding for implementation, it would go away. And now what we did is we took that model as our complement, and then we refit using Lasso credibility on the large state, the medium, and the small state. And at the same time, for the large state, we will take GLM model, a Lasso model, as well as the Lasso credibility model. And then for medium and small, we just fit GLM and Lasso credibility to compare what's happening. And so what this case study aims to demonstrate is several things. One, how does a Lasso credibility model compare to GLM and normal Lasso models? In this case, you can think of a Lasso model as one where your complement of credibility is always null. It's just squishing it to zero as opposed to squishing it to a complement. And then how does Lasso credibility behave with a good complement? How does it behave with a poor complement? Because we're going to have complements of various accuracies. And it's very important to know when you're using a methodology like this, what's going to happen. And the answer, unsurprisingly, should be it follows all the benefits of a credibility technique and all the drawbacks when you use a credibility technique with a poor complement. And then what are the benefits and the limitations? And so these are all things that are gone over in the case study pretty robustly, but I'm going to summarize the behavior here just to show what it does. So this is an example of a categorical variable using Lasso credibility and GLM. And so what we have here, that dark green line is the complement. That is the results of our countrywide model. The GLM is in gold. That's our relativities. And these are pretty much exactly the observed relativities. And Lasso credibility is in light green. And so we can see here on fireworks specifically, we have our complement that was really high. We have our experience from our GLM that's incredibly low. And then we have our Lasso credibility estimate that is in between those. And in this case, pretty darn close to the true estimate. And this is a good result. On the other hand, we have real estate, second from the right, where our true estimate and our complement were actually perfectly accurate, but our experience was really bad. And so at this level of credibility, we did trust that. And we moved a little bit towards that indicated factor, which was further from the truth. It's still better than our GLM estimate, but in some cases, yeah, you can move further away from what is quote unquote true. And then on the far right-hand side, retail is an example of where we decided that these differences were very close. The model completely collapsed to the existing relativity, whereas the experienced relativity was actually closer. So there are some drawbacks, there are some benefits, but I'll say that overall, these Lasso credibility models perform quite well. So when we're comparing to a GLM in aggregate, this Lasso credibility model performs quite a bit better. I believe this is on the large state data. Yeah, so it's using that prior assumption to inform, even though some of it might be slightly away from the true. In aggregate, this credibility weighted assumption is better than a GLM at predicting the true risk relativities. And when we can expect that because we're informing our decision with an informed estimate. We're using a pretty good complement. And so instead of giving true 100% value to the data, we're giving some of that to a good estimate, and kind of expectedly, we're getting a good result. It can also outperform Lasso. So if you're building a Lasso model, you can think of this essentially as a Lasso credibility with your complement being zero, with nothing. And it does, again, make very intuitive sense that if you're weighing something with nothing versus you're weighing it with a good estimate, the good estimate's going to perform better. And that's what we see here. We see that it is, in fact, performing better. So these two results are not unexpected, I would say. I would say that if you use a credibility procedure, it's better than arbitrarily assigning full credibility. If you use a good complement, it's better than no complement. Cool. I mean, this makes a lot of sense. But the power of this comes from when we have data that is way too small to even build a GLM. So on those small data sets, maybe we could like really coerce a model out of that data set. It would be pretty bad. Most of our coefficients had an extremely high p-value that they would have to be removed. So I didn't even bother really uh, spending the hours and hours and hours it would take to make that model make sense. But what I'm comparing here is our countrywide complement to this credibility weighted prediction, to this Lasso credibility model. And so this is an exercise that probably some of us have seen, is where we have this countrywide model, we have these very small states, we can't really do anything with it. And so we just say we're adopting the countrywide model. We're adopting this big model because we can't identify things that are different in our smaller data set. What this result tells us is that we can get a better model than the complement on data that is too small to build a GLM. And so the takeaway here is that some credibility is better than none for this small data. We want to take what we can, and maybe that's small deviations, and that'll make our model better. This is also an example that you can apply in small, in like maybe if you're using an ISO rating or an industry rating book, or you've adopted rates from a competitor. This is, I would say, a key usage of Lasso credibility is identifying those credible differences across all of your variables. And especially if you're doing something like commercial auto, yeah, you're going to have a lot of industries where you just don't have the credibility to deviate, and those will collapse completely. And so here, we really want to be able to take what we can from our data. And that's some credibility, then none. I read that it's a really important point, and that's actually the title of one of our chapters at the end of this monograph. So what do we do with this? Some credibility is better than none. Cool. But then I'm talking all about pricing so far. I'm talking all about this single example, but what do we do in practice? What does this look like for your data that is, again, not simulated? Maybe you have different subsets or different sizes of data. So if you have huge data, if you're the State Farms, the Allstates, the Progressives of the world, I'm sorry if I didn't name your company, but those are the ones that I see a lot of commercials for. If you see these big data, maybe you don't need a complement. You're like, ah, lasso credibility. That's very silly. Um, but when you have medium data, you can't really build a model without a complement. You can satisfy ASOP 56. You can bring in your complement and build a rating plan for implementation. You can build a pricing rating plan. But then with small data, what do you do here? Maybe it's even a little bit too small to implement, as we were looking at before, where we don't even want to take the results of our model and implement it. What can we do with this? And what I'll say is it's time to stop staring at dashboards. Stop using your pivot tables to cut and be like, okay, I think it's this segment that is my problem. This is maybe what happened in Texas in this last year. Something like this. Just stop staring at dashboards and use this for your monitoring and your analysis. So rather than building these models for implementation, because these models are so quick to build, you can build these for the purpose of analysis. You can say, what's going wrong in my book? You can run this model on a subset of data, maybe just your most recent year. And well, you can identify those problems. You can identify what's going better, accounting, or what's going better or worse, accounting for credibility, accounting for correlation in ways that your dashboards and your loss ratio analysis just simply won't do. Additionally, we can start subsetting our data. So let's say you have big data and that's your entire data set. Well, you can subset it. You can say, okay, I'm going to build a model that's on a smaller data set that's for implementation. And I can even subset that more and say, I'm going to analyze this small item. And so what this looks like is we have different data standards for different types of analyses. And I'd say we can really play around with that credibility aligned with the intended purpose. This is something that's really reiterated in ASOP 56 a lot. It's like you need to have a model that's aligned with the intended purpose. It needs to be sufficient for its intended purpose. So what are these intended purposes that I'm getting at? So you can think about this yourself for a minute. You can try and fill in these gaps of what do I have that's big data? What do I have that's a subset of that? Or maybe what do I have that I don't really trust to model completely? What can I use as a complement? And so here is my example. Again, very US centric, but we have our personal auto and countrywide. We have maybe now we can fit a model to our Texas data using the countrywide as a complement. So rather than doing a complete refit from scratch, what we're going to do is just say, okay, where is Texas different from countrywide? Maybe I have enough data there to make this analysis. And then I want to build a model maybe just on 2022. See what's going wrong in that year, what experience is happening. Now, I would not implement this model. I would not say this is my new pricing model. It'd probably be a fantastically bad choice. Single years are noisy. But if someone asks you the question, what went wrong in this year in this state? You don't have to stare at dashboards forever. You can use this approach. It'll identify the variables and areas of those variables that have beneficial or adverse performance, and it'll display those really immediately. And so the same thing can be done if you have medium data. Maybe your complement is your ISO rating plan, and you model off of that. And then maybe your deviation is now you switch complements and you use your original model instead of ISO as a complement for Texas, or you can just use your ISO as your complement for Texas itself. It depends on your analysis. It depends on what you want to use as these complements. And then maybe you have a very small condo book. All you can do is analyze. You're never going to like build your own model this year. You can still use this as a method for analysis. So what does this mean for your pricing department? So what can you do with this information? So first thing I would say, there are no more modeling versus non-modeling pricing actuaries. You don't have to draw this distinction. Everyone can use this technique. It is just a credibility procedure, as I said, but it is also a modeling procedure. Because of that, you have to know enough data science to be able to apply your actuarial judgment. So I'm not saying that you need to be the biggest expert in data science to use this technique, but you do have to know about cross-validation. You do have to know about what could influence likelihood given your select distributions. You should know enough to apply your judgment when using this methodology. I think that reaching exam PCPA is more important. And if you've already got your credential, this continuing ed is what's going to be important, is really building on that solid foundation that you have. And really, this exam, I think, is a great benefit to the exam process. for the US specifically for the CAS. And then communication, you still have to explain it. So I think this is a very simple model. I think these visuals as relativity plots really help you explain this. Because it's a credibility procedure, you can use the same language of complement and indicated, but you still need to be able to explain it with the same level of accuracy as before. Technology, we can move a little bit more away from Excel, a little bit more away from just displaying dashboards and using some judgment. We can really get to a more technical analysis. And so why do I say this is moving towards a more European actuarial? Sorry, as I blow my nose. My daughter's in daycare for the first time for a couple of weeks, and I'm just going to be sick for the next year. But all that being said, okay, why are we moving towards a more European actuarial department? The reason that this is happening is because in European actuarial departments, what I've seen is that they're way more focused on modeling. There's really no distinction between the modeling and non-modeling pricing actuaries. Now, I think my theory is that this has a lot to do with regulation. We have a lot more separations in our process because we don't want to file a model every time we take a rate change. Like there's just some barriers there. But because of the simplicity of the analysis, like I said, there's already regulatory guidance around this analysis. I think this is one way to really move towards using those data science skills in everyday analysis. And so we want to move towards this section where everyone can do everything. Everyone has the expertise to evaluate these models and to use your new tools. And so how I think this can impact actuarial pricing is really it can remove a lot of this prioritization dilemmas of indication versus segmentation. I met with a lot of insurers over the last couple of years, and a common refrain was that inflation is killing us. We don't have any time to do a segmentation analysis. Like there's just no way. If we're underpriced by 20%, why would we bother investigating and building a model? And what I'll say about this is that these models, because they're very quick to build, I say we can really limit that prioritization dilemma, build a one-step model, see if there's something you want to address, and move forward very quickly. Because again, it's just a credibility procedure when applied this way. And this brings me to that fourth bullet point is there is already, again, some regulatory guidance out there on how to review this model. I'm not a regulator. I can't promise that your models will be approved instantaneously. But what I can say is that my personal opinion is that the review process, the validation process for Lasso credibility should be significantly faster than building a model from scratch. I personally believe that it can be reviewed in about the same time as traditional credibility procedures, and that's my opinion. I would love to see that in practice, but I would say that at the very least, this should take less time than a full model filing. For resource constraints, I would say that this process fits very well within the skill sets of traditional actuarial work. It is a data science process, but the upskilling to get to this level is not a large amount. And then when we're talking about bureau rating, one pushback against models as well, we don't have the credibility. Some credibility is better than none. You can get something out of your data that maybe you haven't before. And then lastly, this communication and inertia problem. Well, we don't want to change rates. We don't want to make changes all the time. We really want to have minimal updates. This has been a pushback to doing complete model refits in the past. And yeah, if you're treating your data with full credibility, you're building a GLM, you have these smaller categories, you're going to get some pretty wide variation as you refit your models, maybe year to year or 2 years to 2 years. Whereas if you use a process like this, a lot of the time you're going to get the exact same results, which is something I'll go on a limb and say you're never going to get with a GLM because again, full credibility, you're never going to get exactly the same factor. But here you can. You know that the changes are motivated and not just noise because they overcome that credibility standard. Your changes can be timely in that you can probably get these through validation internally very fast, hopefully externally very fast. And these changes are minimal to the extent that they need to be. Again, you can reach full credibility in this technique or very, very, very close to it. But where there's not significant signal, where your rating plan is not on fire, you will have these minimal changes as you get closer and closer and closer to your experience. So that is what I will say from this is that I do think that this has a chance to really change the way that we do rate reviews in the United States, to really look at everything at once, stop using dashboards, stop using a whole bunch of one-way analysis and hand waving away correlations. We can really look at everything at once in a structure that's based around credibility that is very much in every actuary's wheelhouse. We all have experience with credibility procedures and already have gone over many of the benefits and drawbacks of this type of procedure. And those benefits and drawbacks carry through. We do have the benefits of reflecting a good complement, and we have the drawbacks of maybe there's no good complement, or maybe we have a bad one. So with that, I'm going to wrap up for today. I'm going to encourage everyone to take some time, maybe write some more questions in the chat. Any follow-ups, I can go back to slides that exist now. But while questions come in, I'm going to share some of these upcoming webinars from Akur8 Academy. On December 4th, we have strategies for pet insurance pricing. What can we learn from other lines of business? That's going to be hosted by Edwin Graham. And then on January 15th, there's a presentation on price elasticity modeling, considerations and theoretical aspects, including European regulation. So those are two of the European actuarial data scientists from Akur8. So let's go through these questions in order that they have been received. Are policies with several renewal terms treated as IID, or is the way that their model incorporates correlation between renewal terms and claims activity? So I guess the way that I would answer this type of question is that policies with several renewals are still within your modeling data set and are usually considered within multiple models and sometimes with full, and usually with full credibility. You refresh your GLMs every year, every 2 years. You're reflecting those anyway. If you do credibility analysis year over year, you're reflecting those anyway. And so I'll say that, yes, there is going to be some correlation between your modeled results and your complement, because some of your data will be in the building of that complement. What I will say is that I tend not to worry too much about that because it's moving year over year towards indicated. You're never going all of the way. And to the extent that your experience is consistent year over year, let's say in that driver age example, your experience is always that high. And every time you refresh your model for 5, 6 years, it's always this really high level. You're going to eventually get to that level. But I'd say that is fine because you're inching in the right direction. And so I'll say that like a policy appearing multiple times in this model or influencing the complement is something to consider. But I'd say it's not a barrier to this. And I'm not sure if that answered your question now that I'm rereading it, but feel free to drop something into the chat if I did not. Excellent. I see perfect. The second one is an incredibly great question. So insurance departments usually ask for p-values, chi-squared tests, confidence intervals, et cetera, for each variable included in this model. You mentioned earlier that Lasso doesn't allow for p-values. Are there other metrics that can be provided at the variable level? And are departments of insurance receptive to that type of support? This is a huge question, and this is something that Sam Kloos at the NAIC has recently been working on a lot. I know that he was at least one of the co-authors of this item called the RGLM appendix. So this appendix, again, was out for review, I think, during the month of September, maybe mid-October to mid-August to mid-September. And it contained regulatory guidance specifically for penalized models. And in this regulation, it recognized the fact that some models don't have p-values. Some models do not allow for confidence intervals, and there are certain substitutes. So within this appendix, they recognize that something like reviewing the factors from k-fold cross-validation models, or looking at the bootstrapped, if you have the computation power and a good method of bootstrapping. It has a lot of ways to look at consistency by variable. And I would say that that has been it's been a real North Star in how these models should be reviewed. And so to your last point of, are departments of insurance receptive to that type of support? I'll say that today and for the past couple of years, most departments of insurance have been receptive to the fact that these don't exist and will provide the support that we can. But this is kind of an ongoing question. In derivative lasso, p-values are just not a great estimate on the coefficient by coefficient level, especially if you're looking at each individual coefficient. Each individual ordinal step, you can imagine, is quite difficult. So I will again say I am not a regulator. I don't know how receptive they are to the NAIC's guidelines, but I'd say if departments of insurance adopt the RGLM appendix and use that to replace or supplement their current model guidelines when reviewing penalized models, I expect this to be a smooth approval process where these metrics will no longer be asked for. And one last thing, I think if you attended RPM or have access to those from last year, the NAIC did give a presentation on alternates to p-values for individual variables, because they do want to look at metrics at the variable level. That is an important thing for regulators. So I hope I've thoroughly answered that question. I would encourage all of you to find that appendix and take a look at it. I think it provides a lot of very good guidance and a lot of very good insight as to where regulation of penalized models will go. Okay, cool. I don't see any more questions coming in. I'm going to stall for one more minute so people can type out those questions. But while I'll wrap things up, I will say that I am expecting this monograph to be published in the near future. It is in typesetting. We've corrected some equations and it should be out there pretty soon. And I'd recommend that you take a look at it. And additionally, there will be code on the CAS GitHub. I need to clean it up a little bit, but you can replicate everything that we've done in the case study on your own after that is shared. So be on the lookout for the publication of that paper. Feel free to reach out to me with any questions or comments on the methodology. And I hope all of you have a great rest of your day. Thank you so much for attending.